Hi everyone, I'm Hong Zhichen, a PhD student in the Department of Computer Science and Engineering at the Chinese University of Hong Kong. Today I'm going to demonstrate our demo work, High-Performance Distributed OLAP on public graphs with Grasper. Note that our full research paper about Grasper has been published in SOCC 19. Please check our full paper for more details. In this video, we will first briefly introduce some background, concepts, and text used by Grasper to help SIGMOD' attendees better understand our systems. Next, we will show a web page to provide good interaction with the users to let them obtain useful insights about where Grasper's good performance comes from. Nowadays, graph data is animal, which is widely used in different areas. As a result, dozens of graph processing systems has been proposed targeting at offline workloads like PageRank, Connect Component, graph matching on large-scale graphs. Relatively, which comes a bit late, but shows a high-speed developing trends. Graph database and graph OLAP system emerge in a large number for online case recently. To achieve online real-time analytics, usually the system should support low latency and high throughput at the same time for concurrent query. Further, the system should be scalable in order to handle the large-scale graph data. However, it's actually a challenging thing to achieve such objectives due to the following four reasons. We use an example to demo the motivation of our work. Figure 1 reports the performance of two existing popular graph databases, Titan and Genus Graph, on one single query. We can observe that several query operators like in has label took too much time for the execution. Generally, the overall query latency is high, which is not acceptable for online workload. So what's the reasons of such performance? We summarize the limitations of existing systems below. For the high latency, the time spent on some certain query step are too much, and the diverse query logic and the data access pattern make the system hard to achieve real efficient processing. For low resource utilization, the non-native graph store is unfriendly for graph querying, and the one query, one thread mechanism is not efficient for the high concurrent query. Hence, we propose 4 design goals as follow for the high-performance OLAP on graphs. Grasper is an RDMA-based distributed system, which adopts a native graph store and a series of new system design to overcome the challenges of OLAP scenario on graph. Specifically, we propose a query-friendly execution model called expert model to improve the query efficiency on graph. We use the public graph model to represent the graph data in storage layer, where the public graph model allows each node's edges takes a set of attributes in form of key value pairs called properties to describe their features. Figure 2 shows how we organize the data layout in memory. The data store of Grasper divided the in-memory space into 2 parts, where normal memory is used to store the graph topology data, and the RDMA memory is used to store the property values for global access with a low network cost. We follow such design because naturally a graph query can be represented by graph traversal with the filtering on the properties as well as another control constraint. For example, the sample query shown here involves all above 3 kinds of queries, where the figure demonstrates how a query executed over the partitioned shards of graph data in a distributed setting. Grasper proposed some new features in order to support those system challenges. To implement it, we proposed a new concept called flow type to achieve the parallel query processing inside one query. The flow type defines the execution flow of each query step in a distributed setting. Sequential defines those query steps whose query logical is independent, which can safely process in parallel with fine-grained execution. Barrier means the step needs synchronization before moving forward, while branch type can be further split into sub-queries for processing simultaneously. Based on that, combined with the query parser, Grasper will construct a logical execution plan represented by a DAG for each query, where each node in the DAG represents one query operator associated with his flow type. Then the execution engine of Grasper will drive the query processing of one query based on his DAG to ensure the execution order with correctness guarantee. The execution engine of Grasper follows a design philosophy called expert model, a top-down query-specific mechanism to address the challenging of Graph OLAP. We provide the following three functionalities. First, adaptive parallelism control at step level inside each query. Second, tailor-rated optimization for various query steps according to the specific query logic and data access pattern. Third, locality awareness, thread bounding, and load balancing. The expert is a physical query operator in Grasper that expertly handles the processing of one category of step so as to allow fine-grained tailor-rated optimization for query, where each expert maintains its own structures for optimization, its own execution function for the specific process. We use the example in here to demonstrate how expert model looks like in the system, where Figure 4 shows the overall system workflow under the concurrent queries on one node. To save time, please refer to the related description in our full paper about this part. Now, let's demonstrate how our system works. We provided a graphical interface to allow users interact with Grasper so as to help them better understand the key design of Grasper and how expert model works to speed up online query. As shown in this web page, at the right control component, people can select one single query to run or a batch of queries for batch processing. We also list the specific system configuration and the dataset info in here. At the bottom right corner, we set a monitor to real-time visualize the CPU and network resource utilization occupied by Grasper servers in a cluster to show how efficient Grasper is in terms of resource utilization. For single query processing, once user confirms which query to run and click the Start button, the web interface will send this query to our backend servers for execution. We visualize the DAG of the current running query real-time at the left side of the main page. We're also showing the standard output from the server side to the console at the middle. The DAG will show the specific optimization query plan of current running query with detailed runtime information, including the parameter, the parallelism degree of each query step on one certain worker, and the optimization applied in each expert, as well as the message routing strategy, if any, as we show now. In addition, we dynamically update the job progress of the current running query at step level in runtime. We'll mark as green and red color for the active and inactive step respectively to demonstrate the mechanism and the effectiveness of expert model. The console will output the real-time system logs and the query latency and the results returned from the server side once a query is completed. In batch processing model, another component will show up to display the real-time throughput for the whole system, which provides a clear view for the performance of Grasper during batch processing. User can click this button to know the specific query template we use for the batch processing, where all query templates come from the LDBC benchmark. Note that to save time, by default, the system will only run 1 minute for throughput testing. We also provide more comparison results by comparing Grasper with another 4 existing systems. For more details, the attendee also can check our full research paper published in SOCC 19, Grasper, a high-performance distributed system for OLAP on public graphs. People also can check the implementation of the Grasper on our GitHub Repo. Thanks.